Here we go with thermal physics. Um, I am going to use the CAM document again as our tick list to make sure we've done everything. Let me start. All right, the first thing is energy transfer or thermal energy transfer. Please don't just talk about heat. You can say heat energy or thermal energy. When an object is in thermal equilibrium, it means that it's at the same temperature. But to get there, energy is always going to go from the hotter object to the colder object. So the object that has more thermal energy towards the object that has a lower thermal energy. So it's thermal energy that is transferred. But when you get this question in an exam, make sure that you mention the objects. You can't just be very vague about it because the question will say, state the direction of energy transfer and say there is a hand touching a hot spoon. Then you must say the energy is transferred from the hot spoon to the beautiful cold hand. So that would be your energy transfer. If you want to make sure, then you can say hotter spoon, colder hand, not just spoon and hand, but whatever is in the question, be specific to the question. And then once they are at thermal equilibrium, it would mean that these two objects now have the same temperature as measured on a thermometer that we'll get through now. So that's pretty simple, I believe. Then you need to be able to recognize physical changes of substances with temperature. So if there's something that could change as the temperature is changing, that could be used in a thermometer or to make a thermometer. So electrical properties are a little bit harder to use than the expansion ones, but we've spoken about it where you can look at resistance. Resistance will increase as the temperature of a substance increase. There's also thermocouples where you're comparing the conductivity, but you don't have to know the details about how these things work. Just know that they can be used as thermometers because they have they've got some property that changes, a measurable property that changes as the temperature changes. It's not always linear as it says there, so then it's harder to make your thermometer because the calibration is getting a little bit harder. But the mechanical properties that we deal with in this chapter, the length and the volume specifically, those are linear changes. And what's nice about that is that you can have then a bottom scale, a top scale, and you can design your thermometer according to that. Pressure could be used in gas thermometers. We don't deal with that so much in this section, but you can still have it as a question. You can still use it as an example. But for us, when you're looking at a normal thermometer, a liquid in glass thermometer that we normally use, there we would have 0 degrees Celsius, which would be our one limit, and then we will have 100 degrees Celsius. And because these points are easily measurable at sea level as the freezing point of water and the boiling point of water. What you can then do is if you have your thermometer at 0 degrees, you will have your bottom limit there. At 100 degrees, you'll have your top limit there. And it's easy to make your thermometer then because it's a linear scale divided up into 100 equal pieces. And there you have your thermometer. So that is an easy way then to make a thermometer. They can calibrate them. And yeah, that's what we generally use. Now, when we look at the different scales of temperature, just throwing these away that we have space. The three scales of temperature that we are commonly referring to, as I said, water would boil and freeze at specific temperatures, so that's always a nice one to have. The Fahrenheit one is not as nice because in the metric system we like using hundreds and tens and thousands. Fahrenheit is not really used in South Africa, and we are not really going to worry about it so much. Just know that it is there. But here, the change in Fahrenheit would not be the same as a change in degrees Celsius and a change in Kelvin, which you must remember is very important. So when the question is talking about a delta T, which it often does in this chapter, you can see that a change of 100 Kelvin is also going to be a change of 100 degrees Celsius, although the freezing point is at 0 degrees Celsius and 270 degrees, 0.15, like you have it on your information sheet. In in Kelvin, the change is the same. The only reason why the Kelvin scale is important for us is because it gives us the absolute zero scale. So what they did, it's a very theoretical measurement. So what they did is they graphed the temperature, and then they realized that the volume of a substance. So when you have a substance and you're decreasing the temperature and you're decreasing the temperature, there's not a real value where that substance can have zero volume. Remember, it's going to contract, contract, contract. So that's why I'm saying it's a theoretical temperature. But if we could reach that point, that would be absolute zero, and that would be at 0 Kelvin. So our temperature in Kelvin would then be zero once the volume is zero. But because that's not really it is a theoretical temperature. As soon as we heat it up, then heat up, you'll have a linear scale as well. And then you're here at 270 3.15 degrees Kelvin, that would be where our normal 0 degrees Celsius would be, that we are used to as our freezing point of water. But why would we do that? Because now we've got a linear scale and we can say volume is directly proportional to the temperature, and this allows for a lot of equations that we can derive from here that we don't really do in further physics, but you will do them when you go to university, where you do the gas laws and all of that. But for now, what you do need to know is, as we just said, to change from degrees Celsius into Kelvin, you are just going to add 273.15. You use the values as given on your information sheet. Be very careful to do that. Moving on. Internal energy, potential energy, and kinetic energy. Do not get confused with these things. So, internal energy is the energy that the particles contain. Total energy of the particles. So that means it's the potential energy that they have because of the bonding and the chemistry that goes on inside. You don't have to know all the intricate details. And then the kinetic energy because of their movement. And it's the kinetic energy that is linked to the temperature. Please remember that. Because if the temperature is increasing, it is the kinetic energy of the particles that are increasing. They're moving faster. The potential energy is changing. That has got to do with the bonding and that what's happening in between the particles. So that is why, yeah, when you have a solid and the solid is just increasing in temperature, then we can have an increase in kinetic energy. But as soon as the phase is changing, that is then going to be an increase or a decrease in the potential energy of the particles. But both of these lead to an increase in the internal energy. And so the two together is going to give you your internal energy. So please, very important, when you have a bunch of particles is just a safe word. It could be gas atoms. It could, if it's a noble gas, it could be a molecule. So I just talk about particles. So if the kinetic energy increases, then that means the speed is increasing, and this is linked directly to your temperature. So the temperature is directly proportional to your kinetic energy of the particles. So the temperature will go up. The potential energy, if the potential energy is going up, that would mean that the particles are now separating from each other. You are overcoming those intermolecular forces, and the particles can now start moving free away from each other. Sorry, I'm just killing all my technology quickly. Now, this was a question from the past paper. It said, which statement describes the changes? Just move some space here for us. Describes the changes in energy when a substance is when a metal undergoes thermal expansion. So they didn't say the metal is melting. So that means the phase is not changing. So that means we're not doing this. We don't have a potential energy change. It's only the kinetic energy that is changing. So please think about the question first, because before you start reading these, because remember they each worth 2 marks and you want to get them right. So they are not overcoming intermolecular forces yet. So when you see something about intermolecular forces, you are going to ignore that. The atoms are definitely not expanding in size. Oh, that's something very important. Remember, the atoms are atoms. You are not breaking them or making them into other atoms. The atoms has a fixed size. The particles are not changing in size. They definitely stay the same. So this should be the rubbish one. Remember, there's always one that's nonsense. And then we are left with these two. The metal absorbs heat energy, that is true, causing an increase in the vibrational motion, which increases the spacing between them. Now, if you we'll get to this now, there is a section on why do solids actually expand. So this could be an option. And then the metal atoms move apart because they are repelled by each other as the temperature increases. No, that is not true. They're not all of a sudden going to be repelled by each other, not more than what they were anyway originally. So the answer is definitely B, and we'll discuss this again a little bit when we're looking at thermal expansion. So yes, they are moving more, and because they are moving more, they are pushing each other a little bit more away, but it's because they're vibrating more, and that is why B would then be the answer for that question. Okay, then kinetic model. So next point in your document, kinetic model is the solid, liquid, and gas that you've done in very low grades, grade 8. You've done this. What's the difference between a solid, liquid, and a gas? I'm really not going to do too much about that. You need to know that when you heat up the particles, they're gaining energy, they form liquids, gaining energy, form gases, gaining energy, form plasmas that we didn't really work with before, but we could, I guess, work with it now. But then here you need to just know the kinetic theory, the fixed shape, take the shape of a container, move freely. You can just read through that in your textbook or just here. There's a lot of this on the internet, but it is stuff that you already know. The phase changes, you should know solid to gas is going to be sublimation if it's direct change, deposition, freezing, melting, vaporization. I'm not really going to talk about that. But then the heating curve and the cooling curve, this is important. So what you need to realize here is here where the temperature, I'm going to make that a little bit bigger for us because that is the one that I actually want to talk about a little bit. So here, where the temperature is increasing, you need to then know that there is the kinetic energy there that's increasing. Again, here, the temperature is increasing. So here, it's the kinetic energy that is increasing. Here, where it's flatlining, we have an increase in the potential energy because now the phase is changing, the intermolecular forces are overcome and they are moving further from each other. The same here again is the potential energy that is increasing. And then at that point again, we've got the increase in kinetic energy. All the time, the internal energy is increasing. Please remember this. When the kinetic energy is increasing, internal energy is increasing, and when the potential energy is increasing, the internal energy is increasing. So that line would just be going up all the time. There was a question like that in a test that I've seen lately. You do need to know the difference between boiling and melting. So although I say that this is super easy and you've done it in grade 8, you've done this in grade 8 as well, but we've seen that people get confused with what the difference is between boiling and melting. No. Why did I write boiling and melting there? Definitely there's a difference between boiling and melting, but let me just fix that. It's boiling and evaporation. That is what you need to know the difference between. Evaporation is because both of them, please, they both change. If you're looking at the diagram, they both change a liquid into a gas. This is liquid, gas. For boiling as well, this is liquid, this is gas. So it's changing liquid to gas, but they are two different processes because evaporation, and that's the important difference, happens at all temperatures. Okay, and it happens slowly. It's not going to happen all at once to all the particles. So it's at all temperatures, and what's important is that it takes place on the surface of the liquid. So this you can mention. No bubbles seen is actually a good. You won't see bubbles if something is evaporating. That could also be a difference between the two. But they both change a liquid to a gas, so that's definitely not a difference. It would be a similarity where boiling is always happening at a constant temperature. Remember, that's latent heat, happens at a constant temperature, and the phase is being changed. So it's where, again, the potential energy is now increasing, actually, for both of them. Then it's definitely at a faster rate, but what is important is it happens throughout the whole liquid, and you will see bubbles forming. One thing that we haven't really spoken about before, and I think that's an important point here, is that evaporation causes cooling. In biology, you deal more with this because the surface particles that are leaving are the more energetic particles, and then the liquid that remains will cause the total kinetic energy of the particles to drop, the total average kinetic energy of the particles to drop, and that would mean that your liquid then is cooling down. So the faster a liquid can evaporate, the faster it can cause cooling. So if you take Q-Tex remover and pour it on your hand, that acetone that evaporates fast will cause your hand to cool down fast. Again, past paper question on this that we had last year. I don't know if it was last year. It's from a past paper. Is they talking about evaporation and boiling again to make sure that you know the difference. So you needed to choose evaporation occurs throughout the liquid. So though that one is wrong because it is exactly swapped around. So it was not one. So we already know that those two. Please remember to answer your multiple choice cleverly. And it's also not all statements are correct. So by default, if you realize that one is wrong, you already had the right answer because now so we can just check to evaporation the high energy molecules from the surface is escaping, but in boiling it's escaping from everywhere. And if you read the rest, you'll see that they're not correct. This is basically a summary that I found. I've put all the sources there in the front and you can go look them up. I did put all the videos on the classroom as well. So yeah, while the solid is increasing in temperature, remember there's an increase in kinetic energy. I just wanted to state that again. That's the kinetic energy that is increasing. So when we get to the calculation, this is where you're going to use MC delta T because there is a change in temperature there for that part. Soon as the phase change is happening, then it's latent heat, then it's the potential energy that is increasing. I'm just talking increasing. Obviously, if we're going the other way around, it will then be decreasing. So that's the potential energy. Now, here is where you're going to use Q equals ML. That's going to give us our temperature. So every time when the liquid is now increasing temperature, again, it's the increase in kinetic energy. And again, if we were doing the calculation, this will be MC delta T again. And so on. So please, and while everything is happening, the internal energy is increasing. So please remember that. So when they're talking about the potential energy, remember that is where we're overcoming those intermolecular forces and the particles are now breaking free from each other. All right, moving on to the next part, to the next tick list. We've spoken about a few of these, but now we are going to look at the expansion quickly. So this is the one that I spoke about earlier, that whenever the solid and the liquid increase in temperature, there's no phase change. So the potential energy is not increasing. It's only the kinetic energy that is increasing. Remember that. So what that means is that these particles in the cold solid are now moving a little bit faster and further away from each other. But remember, they're still vibrating in position. It's still a solid. So this was a solid and this is still a solid. There's no phase change. So that increase in temperature is still going to be, if we're doing a calculation, mc delta T will be the energy that we are adding here. And only because they are vibrating more, they are pushing off each other a little bit more and they make spaces for each other. So this has been asked in a few papers, and that's why I just put these points here, because they do expand very little, some more than others because of the constants, but we'll get to that the expansion constants now. But it's because the particles are moving faster. It's not because they're breaking free from each other. In a liquid as well, here they are rolling over each other. In the cold liquid, they are rolling over each other. Yeah, they are also rolling over each other, but because they are moving faster, they will again push away more from each other. They're vibrating more, they're rotating more, all the movement is more. And that's why they are expanding in the liquid. And that is the thermal expansion then from about for solids and liquids that is used in many, many applications in real life. And these are the two that you need to know. There is area expansion as well, but we are not going to focus on that. We've got linear expansion. This is the equation that is on your information sheet. So don't go and learn any other equations. I see too often that people learn equations and then they get it wrong. And this one as well, the on your information sheet. So if it's just length we are looking at, then please remember L naught is your original length of your ruler or whatever you are using to measure this. And then delta L is just that change in length. The same with volume. V naught will be your original volume, and delta V will be that the extension, the actual expansion that happened. And so that's original. That is what is increasing by. So if you want the new volume, you calculate this and straightforward add it to your original volume or to your original length. So the new one plus the old one is going to give you, the extension plus the original length is going to give you the new length. But use this equation because this is the one that is on your information sheet. The coefficient of expansion for linear expansion, we use the alpha. For volume expansion, we use the beta, and you'll see that always the linear expansion is going to be a third. You can think of it, volume is three sides, yeah? So three lengths basically that is expanding. So this is going to be 3 times the linear coefficient of expansion. And then it's plug and play. The only thing that you must be very careful about, if you are using centimeters on this side, make sure that you are using centimeters on this side because the units need to cancel out to give you the correct answer, because otherwise you are using different factors. The same here, if your volume is in centimeters cubed, then the original volume must also be in centimeters cubed. So this type of experiment can be used to determine circling the wrong thing, to determine the coefficient of linear expansion or the coefficient of volume expansion. So that could be a graphing question. And at the end of this chapter, or at the end of this, I'll put all the options for graphing questions that you could get there. Okay, you need to mention practical examples of thermal expansion. We've spoken about these before. there's many things that you can look at. You can go and read through these. You can also go and Google and find some extra ones. The one that is most common is the one that we're using in our thermometers. Railway tracks, they leave those little gaps, joints in bridges. They use it in the aeroplane industry. They use it everywhere, for especially where metals are concerned, because they expand a little bit more than other substances. Then you'll see in your CAM document, you need to be able to explain why water and ice is a little bit weird when compared to other substances, because they don't behave the way they should. Water, so normally when you take a cold substance and you heat it up, that would mean that it expands, expands, expands. But the water behaves a little, it does that to the biggest extent, but there's a small temperature range where water behaves weirdly, and that is very important for us because as the water contracts when it's cooling, it when it reaches about 4 degrees Celsius, and it is all about these special hydrogen bonds in water. When it contracts, the warm water will the warm water will contract, 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 and then when it gets to about 4 degrees Celsius, that is actually the densest that the water gets. Okay. And then what happens is that when it goes between 4 and 0 degrees, the hydrogen bonds actually forms. I always think about soldiers in a line. If they're standing all mixed up in a bundle, they don't take up that much space. But then when they align themselves in those rows that they always stand in, then they actually take up more space. And when the particles are aligned in the ice structure, and you can think about a snowflake as well, they now take up less, or they expand because there's more space between them, and that means they become less dense, and that means that ice then will float on water, which is amazing for us because now below this ice we could still have plants and fishies swimming around so that they can stay alive in the water here. Okay, I just put these points here if you wanted to go and learn them. All right, specific heat capacity. These are the calculations now. So when we deal with energy transfer, when we're transferring energy, and I've put this little graph in here again because remember, when we are looking at the phase changes or the cooling heating graph, here is where we have the EK. So this will actually be kinetic energy. So the thermal energy would be gained as kinetic energy because there's a delta T. So here the temperature is increasing, there is a delta T. Here, delta T is 0, so there is no delta T. So you know this is where I'm going to use my latent heat. So here, the energy that I'm gaining here is going to be EP because that energy is now being used to overcome the intermolecular forces. And then here, there is a delta T again. So it's MC delta T again. Here, it's ML and so on. Here, there is no same temperature. So it's going to be ML again. And here, it's going to be MC delta T. I'm not going to do this in detail because we've done a lot of these examples, but this is now when the question is asking about energy. How much energy do you need to raise the temperature of a substance of 1 kilogram of a substance by 1 degree Celsius? That energy there is then the energy that we need, and the C is our specific latent heat. So that's a constant that you can look up that we normally give you, or we could give you everything else and we can ask you for that constant, the specific heat capacity. The latent heat, we've got two. We've got latent heat of fusion and we've got latent heat of vaporization. So when we are changing from a solid state to the liquid state, it's then fusion, or when we take changing from a liquid into a gas, that's going to be vaporization. So you've got both those definitions on your information sheet. Not on your information sheet. You have both those definitions in your textbook. Just remember that this one happened is a change of temperature, and here the phase is not changing. So please remember that. Here the phase is constant. So you can see here, this is still solid. The phase is constant. Here the phase is changing. So this is a change of phase, but it's happening at a constant temperature. So again, if the question is asking for the difference between these two things, the one happens at there's no phase change, and in the other one, there's no change in temperature. But yeah, otherwise it's plug and play again. Just make sure that when you're looking at change in temperature, please remember a change in temperature. If the change in temperature is 10 degrees Celsius, that change in temperature is also 10 Kelvin. It is not different in Kelvin and or in degrees Celsius. Too many people fall in that trap in an exam. So we just left with some problems. I know I've gone fast, but you can always go back and look at the more detailed videos that I've posted for you. The last 2 points in the CAM document is solving problems. So if it's just a plain heat capacity problem, I've put the answer in here to make it a little bit faster, but you guys can now go and do this and see if you get to the same question, to the same answer. It says here 500 grams of ice is removed at -10. Calculate the thermal energy that must be transferred to melt it. So please remember that you need to change the temperature to the melting point first. So we are always going to, and it should say where it's melting. So we're just going to assume that the melting point is going to be 0 degrees Celsius. So what we need to remember is that it's going to heat up. So there's going to be a change in temperature. So we're going to use MC delta T. Then the temperature is going to stay the same, but it's going to melt. So that's going to be plus ML. So the Q, the energy that we need to gain, is then going to be those two energies added up. Just make sure you can see here you've got kilojoules. So your answer here is going to be in kilojoules. Here we've got joules. So please, that's kilograms and that's grams. So I specifically chose this one so that you can see that that's sometimes one thing that you need to look out for. It's where you need to convert your units. The degrees Celsius doesn't matter because a change in temperature in degrees Celsius is the same as a change in temperature in Kelvin. If you want to change them all to Kelvin all the time, you're welcome to do that. But don't give yourself a place to make a mistake. Now we're just going to fill in our values. If you choose to work in kilograms, then you need to change this value into kilograms. So that would become 0.5. If you do everything in grams, that's absolutely fine. But then you must change this one into grams here. Sorry about that. So I've got the answer here. You guys can go and fill in everything. See that you do the conversion correctly. If you left this one in grams, that is absolutely fine. If you got it in joules, you could convert it into kilojoules again. In the end, just make sure that when you're adding something, if you're adding kilojoules, then you must make sure they're both in kilojoules because we can't add apples and bananas. Make sure the units are the same. And so that was our ML. We would use a capital there. And then here we've got Q is MC delta T. Again, you multiply everything in. You put your constant in there. Make sure your units are the same. Here they used it like this and made sure that all the units are cancelling out. That's also a way you can do it. That is absolutely fine. Please remember, this sometimes leaves room for, I just always say temperature is a scalar. So take your high temperature minus your low temperature because it still will give you a delta T that is 10 and your answer will be exact, will be fine. It's not wrong to do this, but be careful that you don't make mistakes with putting negatives in the wrong places. So very much the case for this one, and I think we've spoken about this a few times. I actually loaded a Khan Academy video for you, but there's other things in that video that's important, where they say that because energy is not energy is conserved, which is absolutely true. You can say the energy in or the energy of the water, the change in energy of the water plus the change in energy of the ice must be zero. Then, if you take that to the other side, yes, it will become negative. But then you must be very careful, as I said before, with your signs. Rather don't do that. But if that's what you want to do, make sure that you're doing it correctly. But this typical question where they're asking for the final temperature, we've got ice that first, so I just put it here. The first step is the ice is changing into water, and then the water is going to our new temperature. So the ice is starting off at 0 degrees Celsius. It could even be lower, it doesn't matter. So you could start at minus and then go to zero, like in the previous example. But I would always say Q lost is equal and Q gained. And then you can put the two together and then you can't lose marks here. So Q lost and Q gained. The lost is going to be of the water. So the water goes from 30 degrees Celsius so it starts at 30 and it goes to the new temperature. So that would mean we're going to use MC delta T for the water. So it's going from 30 down to the new T. This is for the water. Sorry, I'm scribbling roughly because I wanted to go a little bit faster. And then for the ice, it's going from 0 up to a specific temperature. So we want to know what this temperature is. That's what the question is asking us for. And if you do a little diagram like this for yourself, we can see that you know what you are doing. So this MC delta T would then be the 10 grams. I would like to change it into kilograms, but this was in grams, so we could leave it all in grams because then all the values are in grams. So we could say 10, and then our C is there because they told us that it's 4,2. And then delta T for the water is then going to be, it went from 30 minus T. So that will be Q lost. Then Q gained, you can do it in one step. Q gained will be for the ice. So the ice needs to melt first. So ML plus MC delta T. So it melts first, where we're going to use the 10 and the L is given to us in joules per gram. So we can leave it all in grams again, plus our MC was the water. Oh, sorry, that the water was 100 grams. I'm just fixing that quickly. The ice is 10 grams. Don't do what I've just done and mix your values up. This is going to then be, because now it's heating up and it's already become water, 4,2, and that's our delta T is now. And this is where we know that it's going to reach this temperature, but it's so from 0 to that temperature. So I would say T minus 0 because delta T temperature is a scalar again, change in temperature is a scalar, and that means that we've got our answer correct. And then you just put the two equal to each other and you solve for T. And I cheated and I have the answer here. So you put the two together and you just solve for T. And then you don't have to worry about negatives and where you are what you need to do because the temperature it's T minus 0, 30 minus T, and you get your answer perfectly right. This was the one from the past paper last year or the year before, I'm not sure, where they asked for the mass of the coffee that evaporated, but exactly the same thing. A block of granite was inserted into a cup of coffee and some of it evaporated. So now we're going to use, I've got the answer here, so I'm just going to talk through it quickly. You should have paused. You can still pause and do it first, but here we go. You also use MC delta T to work out the energy that the ice is losing, that the granite block is losing. So that was a first question. That's normally a lower order question that's asked first. And then you put the energies equal to each other again. Put your change in temperature. This one was a little bit easier, but specifically because people put negatives in here, the mass ended up being very weird. If you end up with an odd maths, please know that you've done something wrong. We try and be realistic in these answers. I know sometimes it's not. So if it's not if realistic, rather move on with your paper. Don't get stuck on a question and then come back later and see if you can get that answer to be a little bit more realistic. But this one was fine because it's just ice blocks. Oh no, it was water evaporating. Sorry. Then I just put in the different graphs. So what I just basically did is I took the equations, put them into the AI, and it gave all the graphs. We've asked many graphs, but there are many more here. So I'm just going to look at one, but you can go and look at all these different ones. For this equation, you can plot a graph of delta L versus delta T. And as I said in the analytical skills question, you can see there's no plus or minus. So that means the left over there, my graph must be a straight line through the origin, and my gradient, change in y over change in x, would then be equal to alpha times by L naught. So this is a nice question where we then could give you alpha, the coefficient of linear expansion, and ask you for the original length, or we could give you the original length and ask you for the linear expansion there. Exact same thing we can do with the volume here. The volume one exactly the same. Let me throw that one away. Throw it away. Same, then this would just be then delta V, and this would be V naught. Scribbling over each other, sorry, that's very ugly. This could be a delta V versus delta T, and that would be V naught. If we give you V naught, well, that would mean that you could then go and use your change in Y over change in X, your gradient value to get B. Please remember, do not go to the table. And so on. You can do that for any of these equations. So there's no real plus or minus, so the chances are that if you get a graphing question in this section, it will pass through the origin, except if we maybe go and add the original length. That could be a little bit different. So this could be the different graphs that you could get. You can pause on this and see if you can figure out how you could do the gradient, but it gives you all of that there. We could give you the latent heat of fusion. Again, if we give you the energy that's added, and this is a nice practical way of doing it because you can use VIT to get the electrical energy that goes in, and that would be equal to M times by your latent heat of fusion. So if you have the mass of the substance, you could use that to get your latent heat of fusion as your gradient of your graph. So that's another option there. I'm going fast, but you guys can go and can look at these different options. And then we also could do the latent heat of vaporization in the same way. So yes, please play around with these graphing questions and see if you can predict what we could give you. And that's the end of thermal physics. Happy studying.